Hey everyone, Mr. Fransky here. I got a video for you about related rates today. Related rates is an interesting topic in calculus, and this is one where it really makes me, I think, more active about the world around me and more aware of what's happening in terms of calculus when I'm looking at different things and systems that work in the world. So today students will be able to solve related rates problems using the four-step system. So, key vocabulary: derivative with respect to t, related rates, chain rule, and implicit differentiation. So we've talked about chain rule and implicit differentiation. Deriving with respect to t is a little bit different. Usually we derive with respect to x. Like if you have y equals 3x squared minus 2x plus 1. The derivative with respect to x, whatever variable is down the bottom here, that's what you're deriving with respect to, would be 6x minus 2. So if you were deriving this like with respect to some other variable, then x would not be what you're deriving with respect to. You'd have to chain a whole lot of stuff. So we're going to see that today in some of our examples. So what are related rates all about? Related rates are about two things that are somehow connected, and they influence each other in the system that they're working in. So, for example, I don't know if you guys have filled up like a water bottle before, like at maybe at one of our filling stations. But if you have a water bottle, let's say like with a narrow neck at the top, and let's say that you have like it's circular, so it's circular around, and the whole, it's like got a uniform radius the whole way up until at the top it gets really narrow. So the water is going in at a constant rate, right? And there's a rate already, right? So it's going at a constant rate, like some volume per minute or volume per second or something, right? And initially, like it's filling at, it seems like the height is changing at a constant rate as well. Have you noticed that when it gets to the top, it fills a lot faster? That height changes really fast when it gets up to the top, right? It's the same like if you've ever like filled up maybe your bathroom sink. So your bathroom sink, if you plug the drain, initially it raises pretty quickly, right? But then as that radius gets bigger, it slows down, even though the constant rate of flow is going in. Somehow those rates are related, right? The rate that it's flowing in and the height, the rate that the height is changing. There's some other problems that you see with related rates a lot. You see things like a ladder sliding down the side of a house is a really common one. So if you have a ladder that's planted against the ground, and if someone's holding it, it shouldn't move, right? But if the bottom starts sliding out, you can think about this, right? Initially, you would have to move the bottom quite a bit to make the top move very much at all. But at some point that switches, right? So like by the time it gets to 45 degrees, now the rate that this is moving should be equal to this rate. And the further out it gets, now it's going to switch. So now you would have to move the part of the ladder that's against the house quite a bit to be able to make the bottom move. And because the ladder is rigid, those rates are related to each other. There's a similar problem like this with cars at an intersection. So if you have one car that's driving, let's say, to the east, and another car that's driving, let's say, to the south, could be a similar problem, right? Maybe you want the distance between the cars to maintain constant. There's also a lot of argument about this. Like if a cop is sitting over here on the road and they're clocking you moving east-west, can they really accurately say how fast you're going? Because at one point, like, I don't know if you've ever seen, like, if you're standing here and the car comes by, like, right, if you're looking at it, think about how fast you have to turn your head, right? So if we're thinking about the car coming this way, think about how fast you have to turn your head. Initially, you don't have to turn your head much at all, even though the car is covering a lot of distance. But by the time the car comes by you, you have to like turn your head super fast as it passes by, right? It's kind of the joke about like if you're watching a race. When the cars go by, you turn your head super fast, and then it's like you're watching them go around slowly, and then they come by and you have to turn your head super fast to get it by. So the rate at which you're turning your head and the rate at which the car is moving, those are all things that are related together. So some of the typical types of problems that you see, the two that I talked about at the end there, are Pythagorean theorem problems, right? So if you have, just remember that x and y, let's call this z, x squared plus y squared will always equal z squared. There are a lot of problems that come up with circles. Remember, the area of a circle is pi r squared, the circumference is 2 pi r. You got a lot of stuff with spheres as well. We're going to see a sphere problem today. So sphere, some interesting stuff. The surface area is 4 pi r squared, and the volume is 4/3 pi r cubed. This is kind of interesting. Look at this. The surface area is actually the derivative of the volume. That happens in a few spots in geometry. It's kind of cool. There's also a lot of problems that involve cones. A lot of problems that involve cones, because if you fill up a conical like glass or something, initially it fills really fast, then it starts filling slower and slower and slower because it's got to create a lot more surface area at the top. And when you have cone problems, 3 things that are important. The volume of a cone is 1/3 pi r squared h. So the radius being the radius at the top and the height being the total height of the cone. And another thing that comes into play a lot is similar triangles when you're dealing with cones. So remember, if you have 2 triangles that share all the same angles, so if this angle is the same, let's say they're both right triangles, that means the third angle must be the same as well. So if you have, like, let's call this h and r, and let's call this x and y. Remember, you can always set up a ratio. There are 2 ways you can do it. You can say, like, maybe r to h has to be equal to y to x. Or you could also set it up with h to x is equal to r to y. Okay? Either way, I mean, really, you're just cross-multiplying here and then resolving it to get it into this ratio. But just some important things that are going to come into play when we're looking at these related rates problems. So let's look at how to actually solve these things. So to solve a related rates problem, this is definitely something you'll want in your notes. The first thing you're going to do is draw a picture with variables in important places. Use numbers only for constants that never change. So like, for example, in our ladder example, something that would never change is the length of the ladder, right? The length of the ladder can't change. So let's say it's like, I don't know, 20 feet. So you would put that on your picture. But the distance down here at the bottom, x, and the distance up here, y, those change as the ladder moves, right? So I would never put any numbers there. Even if they give me numbers in the problem, I would never put numbers there because they can change. List what we know and what we want and what we need. Usually what we know are things like we know what the rate of one part of the ladder is moving or something. What we want might be how fast y is changing. And then what we need an equation that relates to rates. Okay, so what we need is always going to be an equation that relates, the variables. Okay. All right, and then reference the variables from your picture here. So what if you're using, like in this case, it would be x squared plus y squared equals, I guess 20 squared is 400, right? So that would be what we need. We need an equation that relates the 2 variables or whatever variables you're dealing with. Now we derive with respect to time. That's important because usually we'll have a velocity or something will be changing with respect to time. Let's say like x is changing at a rate of like 5 feet per second, something like that. That means that I'm deriving with respect to time because everything is a function of time. So really these are functions of time in here. This would be y of t. Because as time marches on, they are changing. So that's why you will always need to change. Just like when we had like xy minus y squared, something like that equals, let's say, like 10. When we take the derivative here, we have to do product on this. So y plus xy prime minus 2y times y prime, because y is a function of x, right? We're deriving with respect to x. If you're deriving with respect to t, often these equations will not have any t in them at all. So like here I would have 2x times, I write this as dx dt, plus 2y times dy dt equals 0. Okay? Because every function in here is a function of time. Now you solve for what you want and plug in your known values. So make sure that you have this in your notes. You might have to pause the video here to get that in. But we're going to use this every time we do one of these problems. So let's take a look at some. So first example, the radius of a circle is increasing at a rate of 2 inches per minute. Find the rate of change of the area of the circle when the radius is 6 inches. First thing we're going to do is draw a picture. We need a circle. Here's our circle, there's our radius. So they tell us is that the radius of the circle is increasing at a rate of 2 inches per minute. So this radius is getting bigger and bigger and bigger, which means the circle is expanding, right? So 2 inches per minute means we're getting bigger and bigger and bigger. That radius is increasing at a constant rate of 2 inches per minute. Then we have to find the rate of change of the area of the circle when the radius is 6 inches. So let's write what we know. We know that the radius is changing at a rate of 2 inches per minute. That's dr dt. The radius is changing with respect to time at a rate of 2 inches per minute. Okay, so that's how radius is changing with respect to time. What we want is the rate of change of the area. We want dA dt, right? So as r increases, initially a small change in r maybe isn't going to change our radius a whole lot, or our area a whole lot, because it's a small circle. But as we get bigger, a small change in radius is going to require a lot of extra area around the outside, right? So what we need is a equation that relates r and a. Okay, so we need an equation that relates r and a. Well, that shouldn't be too tough, right? A is equal to pi r squared, right? So that's an equation that relates a and r. Now we're going to take the derivative of everything with respect to t, right? So we do have a picture. We listed what we know, want, and need. That's what we have right here, right? We know, want, and need. And we now derive with respect to time. So the left side here isn't too bad. It's just dA dt. Right? The derivative of area is just derivative of area. And that's going to be equal to pi times 2r, so the 2 comes to the front, now we change, times dr dt. So again, remember this is a of t, right, because area is changing as time increases, and this is r of t squared. So the 2 came to the front, and then I took the derivative of r with respect to time. So every time you do this, you're going to have to chain. Now, what we're going to do is we're going to solve for what we want. Okay, so we want dA dt. We know everything else. Let's plug in what we know. Find the rate of change of the area of the circle when the radius is 6 inches. So I know that r is 6, and I know that dr dt is 2 inches per minute. So I just plug in the pieces. So dA dt at that moment, because at different moments the area will be increasing at different rates. At that moment, I'm going to have pi 2r, r is 6, times dr dt, which is 2. So that is 2 times 6 is 12, times 2 is 24 pi. That's a change in area with respect to time, so that'd be square inches per minute. There we go. That's all there is to it. All right, let's try another problem. The volume of a sphere is increasing at a rate of 3 inches cubed per minute. Find the rate of change of the radius when the radius is 10 inches. Okay, so let's draw a picture. We got a sphere. There we go. And they tell us that the radius is, sorry, I'll just put an R there because it's increasing. So they tell us the volume is increasing at 3 inches per minute. So that's what we know. dV dt. We know how the volume is changing with respect to time. It's changing at 3 cubic inches per minute. Now, this is maybe more realistic, right? Like, let's say this is a balloon. Okay, let's say this is a balloon, and you're blowing it up. Every time you release a breath, it's a constant volume of air. So maybe you're increasing the volume by 3 cubic inches every minute. You could probably do better than that with your breath, right? But the volume is constantly changing. Initially, that radius is going to be getting bigger a lot, really quickly. But as the balloon gets bigger, your air is going to only increase the radius slightly. Right? Even though the volume is increasing the same amount, the radius is only increasing slightly because a little air is only going to add a small, thin layer around the outside of the balloon, right? What we want is how the r is changing, dr dt, right? They ask for the rate of change of the radius. So what we need is an equation that relates, we need to relate v and r. Okay, so we need an equation that just has a v and an r. Well, thankfully, the volume of a sphere is 4/3 pi r cubed. Okay? So now we derive with respect to time. So dv dt is equal to, that 3 comes to the front, so I have, the 3 will come to the front, it'll actually cancel, but let's write it this way. 3 times 4/3 pi r squared. Then we must multiply by the derivative of r with respect to time, dr dt. You'll notice I'm using Leibniz notation for all of these. That's because this dr dt, it's weird to write r prime because we're introducing like a new variable, right? There are no t's in the original equation, and now I'm deriving everything with respect to time. Now we plug in what we know. We know that dv dt is 3 inches cubed per minute, so this is 3, equal to, these canceled. So we have 4 pi, and they tell us at this moment the radius is 10 inches, so it's 10 squared times dr dt. That's what I want to know. So let's see here, 4 times 100, so we have 3 equals 400 pi dr dt. So dr dt is 3 over 400 pi. And let's think about units here. That would be, so radius is a linear. It's going to change at inches per minute. Okay. So that's what I've got for you here. You may have noticed in my room, there's always someone playing with them. Let's see if I can end the show here. There's a Tremel of Archimedes. The Tremel of Archimedes is a little, it's a toy really. And every time I see one of these, I think about related rates, because I like just like we were talking about with the cars. As one thing moves, right, it's moving at different rates, right? It's fast in the middle and slow at the edges, and the other one pretty much moves the exact opposite way. They're connected by this bar, right? And so the rates must somehow be related, and the math on this is actually pretty interesting. If anyone wants to come in, we can chat about it. The edge of it, the outside of it, actually ends up tracing out a perfect ellipse. You can prove that using parametric equations, and the rates that these things move are pretty fascinating. So if you ever want to come in and chat about it, you can. Otherwise, though, that's the theory and the practice behind solving some of these related rates problems. I'm going to do the other 3 problems on your sheet in the next video if you'd like to see that. Otherwise, just practice, practice, practice. Lots of problems, and you'll be in good shape. Love you guys. That's why I'm here. Have an excellent day.